Today, we're delving into a research paper focusing on a human-in-the-loop reinforcement learning system for precise and dexterous robotic manipulation. The authors claim to achieve near-perfect success rates on complex tasks with surprisingly short training times. What are the key challenges in achieving human-level dexterity in robotic manipulation, and how does this paper address them?
The core challenge lies in the sample complexity of reinforcement learning, RL, in real-world robotics. High-dimensional state and action spaces, coupled with the need for extensive trial and error learning, often lead to impractically long training times. Furthermore, designing accurate reward functions for complex, dexterous tasks is notoriously difficult. This paper tackles these issues by integrating several key components: a pre-trained visual backbone for stability, a sample-efficient RL algorithm, RLPD, to reduce data needs, and crucially, a human-in-the-loop system for corrections. Human feedback guides the learning process, allowing the system to learn from mistakes efficiently.
The use of a pre-trained visual backbone is a common practice now. However, what specific advantages does it offer in this context of real-world robotic RL? Why not train the visual component end-to-end?
A pre-trained backbone, like ResNet 10, pre-trained on ImageNet, provides several advantages. First, it offers improved optimization stability. Starting with pre-trained weights avoids the risk of the visual processing component getting stuck in poor local optima during the RL training process, which is particularly crucial in real-world settings where training time is limited. Second, it improves exploration efficiency. A robust visual representation allows the RL agent to focus its exploration on more relevant aspects of the task, rather than wasting samples on learning basic visual features. Training end-to-end would require significantly more data and computational resources, making it impractical for a real-world deployment.
The paper mentions RLPD. Could you elaborate on its role and why it was chosen over other sample-efficient RL algorithms? What makes it particularly suitable for this human-in-the-loop approach?
RLPD, reinforcement learning with prior data, is chosen for its sample efficiency and ability to effectively incorporate both offline data, human demonstrations, and online data, robot interactions. It achieves this by equally sampling from both data sources during training updates. This is crucial in the human-in-the-loop setting because it allows the algorithm to leverage the knowledge gained from human demonstrations while simultaneously learning from the robot's own experiences and corrections. Other algorithms might struggle to effectively combine these two data sources, leading to slower learning or instability.
The human-in-the-loop aspect seems critical. Can you detail the process? How does human intervention affect the learning process? And how is this data integrated into the RL algorithm?
The human operator can intervene at any point during a robot's trial, taking over control via space mouse to correct errors or guide the robot towards success. These interventions are recorded and stored in both the demonstration and RL buffers. However, only the robot's actions before and after the intervention are added to the RL buffer. This ensures that the RL algorithm learns from the robot's mistakes and the human's corrections, but doesn't simply memorize the human's actions. The human intervention frequency decreases as the policy improves, transitioning from heavy guidance to autonomous operation.
The paper showcases impressive results across diverse tasks, including dynamic manipulation, precision assembly, and dual arm coordination. What specific design choices beyond the algorithm itself contributed to this broad applicability and high performance?
Several system-level design choices were crucial. The use of a relative coordinate system for proprioceptive information allows for spatial generalization. The policy isn't tied to a specific location in the workspace. A well-designed low-level controller, impedance controller with reference limiting for safety, ensures safe exploration during training. For gripper control, a separate critic network handles discrete actions, simplifying training and improving performance. Finally, the sparse reward function, based on a trained binary classifier, provides a simple yet effective way to guide the learning process across different tasks.
The paper compares HIL-SERL against several baselines, including imitation learning methods. What were the key findings of these comparisons, and what insights do they offer into the relative strengths of RL versus imitation learning in this domain?
HIL-SERL significantly outperforms imitation learning baselines, HGD Agar, in terms of both success rate, average 101% improvement, and cycle time, 1.8 faster. This highlights RL's ability to self-correct and optimize for task-specific rewards, overcoming limitations of human demonstrations. Imitation learning methods, even interactive ones, struggle to achieve the same level of performance and robustness because they lack the exploration and optimization capabilities of RL. The gap widens for more complex tasks, where human corrections might be less optimal.
The analysis section delves into the reliability and learned behaviors of the policies. What are the key findings regarding the reliability of the learned policies, and how does this relate to the funnel concept discussed in the paper?
The high reliability, 100% success rate on most tasks, stems from RL's self-correction mechanism. The funnel visualization shows how the policy progressively concentrates state visits around successful trajectories, creating a robust region connecting initial states to the goal. This contrasts with imitation learning, which lacks this self-correction and results in a more diffuse state visitation distribution. The funnel represents the policy's increasing confidence and precision as it approaches the goal.
The paper also distinguishes between reactive and predictive policies. How does HIL-SERL learn both types of policies, and what are the implications for the types of tasks it can solve?
HIL-SERL learns both reactive and predictive policies within the same framework. Reactive policies, characterized by high action variance near the goal, are suitable for precise manipulation tasks requiring real-time adjustments. Predictive policies, with low action variance, are better suited for dynamic tasks requiring consistent open-loop behaviors. The ability to learn both types demonstrates the flexibility and generality of the approach.
The paper mentions several additional baseline comparisons, including methods that leverage demonstrations. How did HIL-SERL perform against these, and what does this suggest about the effectiveness of its approach to integrating human data?
HIL-SERL consistently outperforms baselines like residual RL, DAPG, and IBRL, even when those baselines are provided with significantly more demonstrations. This highlights the efficiency of HIL-SERL's approach to integrating human data. Unlike methods that heavily rely on the quality of initial demonstrations, HIL-SERL uses demonstrations to bootstrap the learning process, allowing the agent to surpass human-level performance through autonomous exploration and correction.
The discussion of the diffusion policy baseline is particularly interesting. What were the key differences in performance, and why do you think HIL-SERL outperformed it?
The diffusion policy, while strong at learning expressive policy distributions, underperformed HIL-SERL on the tasks requiring reactive closed-loop behaviors. This suggests that simply learning a rich policy distribution isn't sufficient for tasks demanding continuous adaptation to sensory feedback. HIL-SERL's combination of RL optimization and human-in-the-loop corrections allows for more effective learning of these reactive behaviors.
The paper concludes by discussing future work and limitations. What are some of the key areas for future research based on this work?
Future work could focus on extending the approach to longer horizon tasks, perhaps by employing task segmentation techniques or improved pre-training methods. Generating high-quality data for training robot foundation models is another promising direction. Addressing the need for training from scratch for each task by pre-training a general manipulation value function is also a key area for improvement. Finally, more extensive randomization and testing in unstructured environments would further validate the robustness and generalization capabilities of the approach.
The paper highlights the importance of careful system design choices in achieving sample-efficient and high-performing RL for robotic manipulation. What are the most significant takeaways for researchers and practitioners in the field?
The key takeaway is that a well-designed human-in-the-loop system, combined with sample-efficient RL algorithms and smart system-level choices, can significantly reduce the sample complexity of real-world robotic RL. This opens up new possibilities for deploying RL-based manipulation policies in practical applications, particularly in high-mix, low-volume manufacturing. The approach's flexibility in learning both reactive and predictive policies further broadens its applicability.
This has been a very insightful discussion. Thank you for sharing your expertise.